Dan appreciates a good landscape, and what I'm talking about are scalar valued functions, and or their graphs. And so for those of you who haven't thought about this, so on the right there's a landscape, and there's you can just think of a function as being the height of the landscape above the ground, and if you just walk downhill you get something called a gradient flow. And many of you are familiar with Lyapunov functions, and some of you familiar with Morse theory, and maybe even a non-zero number of you familiar with Conley's generalization of Morse theory. And so I thought I'd talk a little bit about Dan's work on this. So what Dan and Elon Ramon did was they figured out how you could synthesize classical dynamics and use this on robots. You find a scalar valued function which goes low where the boss tells you to go, and it goes high where the boss tells you not to go. And what Dan and Elon did is they showed you could actually, not only do such functions always exist where they only have one global minimum and hence only one local minimum, you can't get stuck anywhere, but they actually showed how you could construct these. They wrote down formulas for these, and they did these for worlds like the top right where you have spherical obstacles, but then they showed how you could warp space, change coordinates, and also do this for these star worlds, star-shaped obstacles. Landscapes can also be used to synthesize hybrid dynamics. We've seen this picture before. So there's this paper, and by designing landscape pieces or funnels and sort of laying one into the next, you can kind of go wherever you want to go. And on the right, you can do a bunch of these, and you can cover the entire available space, and that's can be a good way to do things. Now, what I started doing with Dan was we wanted to think about, can you use landscapes to analyze hybrid dynamical systems, which people use to model robots, for example, or perhaps the prototypical example is a bouncing ball. And the first thing I did here was with Paul Gustafson, who's in the audience, and with Dan, we wrote this paper, and what we showed is that for not all hybrid systems, but for many of them, these landscapes always exist. So that's the landscape for the bouncing ball, or one of many possible landscapes. So the x-axis there for the bouncing ball is the vertical position. I'm ignoring the horizontal coordinate there, and the y-axis is the vertical velocity of the bouncing ball. And so it comes down, it hits the ground, and then the model makes the velocity reflect, and it just keeps doing this over and over. And no matter what, you're always falling down that landscape, both when you hit the ground, when your velocity reflects, and during the continuous mode of the dynamics where you're falling through the air. And the way that we did that was we took the state space of a hybrid system. So there's this region where you're like hitting the ground in the bouncing ball example, and here's the region where you're falling through the air. And what you can kind of do is you can play some topology games, and you can take this ground hitting region and stretch it up and then glue it back into state space where according to some map that encodes the dynamics, and then you can apply some classical results and deduce that these landscapes always exist. And just to show you that there are some theorems, here are some theorems, but I'm not going to talk about them. Okay, so why would you care about this? Well, something that Dan pointed out to me was, well, now that you know they exist, if you want to find them, now you have a hunting license, is the way Dan put it to me. You are guaranteed that you are not searching for something that does not exist. But there's another reason, and so for those of you who have studied Morse theory, there is a extremely profitable interplay between topology of the underlying state space and the dynamics on the space, and it's a double-edged sword. You can use topology to study dynamics if you know more about the topology, or you can use the dynamics to study the topology if you know more about the dynamics. And that's just an example. You kind of vary on the right, you sort of vary the sea level height and look at how things change, and if you, that interacts in interesting ways with the gradient flow, and you might imagine being able to do something like this for hybrid systems as well. Another thing that I did with Dan about landscapes that I found interesting was we actually used landscapes to show that you couldn't do certain things. So for example, suppose you want to stabilize some subset via feedback control, or suppose you want to choose a feedback control that makes your system operate safely, that is, doesn't run into any obstacles. then because of topological obstructions, you might not be able to do that. And the way that we did that was we said, suppose that you can do this, then there's some hypothetical landscape, and you can study its properties and basically get a contradiction. How am I doing on time, Noah? Over? Okay, I'm going to just go to the end. So we showed that you could not make the systems operate safely or stabilize by studying landscapes. Skip some details there. The thing I'm working on now is a generalization of that, or I just finished rather, and that's it. So here are all the ways I know how you can use landscapes. And so I want to thank you all for listening, and thank you, Dan, for everything and letting me think so much about landscapes.